All right, thanks. I'm Tyler Groff. I'm giving this talk on behalf of a lot of people that worked on this, the notable people that contribute. There were more people contributed, obviously, through all of CGI, but these are the people that really contributed the data and figures you're going to see in this talk. All right, Roman chronograph doesn't need any introduction, but Goddard actually did build and deliver the direct imaging, 2 Wollaston prism and 2 spectroscopy modes in CGI. We made it. We're talking about spectroscopy on CGI. Kind of magical. Notably, I will also say that the imaging and polarization optics were very generously contributed by JAXA. And those Wollaston prisms are actually, as optical specs go, very special elements. So thank you to them as well. All right, so this is the actual image of the DPAM here with those 5 modes individually labeled. The ZOD, or zero optical deviation prisms, are the 2 spectroscopy modes, which are 2 different designs optimized for bands 2 and 3 in CGI. And then the Wollaston prism assemblies are actually the exact same optical design, but with the prisms rotated 45 degrees to each other. So you get 4 different polarization states when you do an observation with both those elements. And then, of course, the direct imaging lens, which is the workhorse for all the wavefront control you see today. The bands are shown here. They work in 10 and 15% respective bands. AJ made a comment about that earlier with those dispersion plots. But note that they all actually function over the entire passband of CGI. So that's something to note for future users. For spectroscopy specifically, this is our objective, our science case is what drove the resolution and band passes that we're talking about here. You can see that nonlinear dispersion curve on the left, where just because we're in a 0 deviation configuration, we couldn't flatten the spectral response particularly well. So this is the best we did, and we tweaked it. You can think of that as an advantage or a disadvantage, knowing in context that this can work in any of the 4 bands, by the way, because what this means, you could use the band 3 prism in band 2 for a higher resolution, or conversely, you could use band 2 and band 3 if you wanted a lower resolution and needed to boost your SNR. So just a note for people who are going to be using this in the future. And on up here is actually an estimate showing the methane, or a model that Neil did showing the methane absorption feature that we're actually really targeting with these modes. So this is just a model of the science case that drove us to build the prisms that we did. Just one quick note on the optical alignment. We accomplished this. We had very tight tolerances on everything, in particular our back focal distance. There's no focus mechanism on the back side of CGI. So we had to guarantee confocality of all of the imaging assemblies in the DPAM to an extremely tight tolerance, much tighter than the F number would lead you to believe. Gary was a real stickler about that. And so this is how we accomplished that, and we've been making sure that through the process we got the right dispersion that we thought we should out of it, just through alignment, where we co-witnessed all of the assemblies during and through the bonding process with a theodolite and an interferometer, and then we also did it in double pass. There's some really clever through and around shots that we did so that we had great confidence that we were building exactly what we meant to through the entire process, from the element all the way through the full assembly level. On the other side of that table was where we actually made a simulator of CGI, or at least a low fidelity simulator of CGI with a OAP relay and broadband tunable source. You can actually see the laser line tunable filter right there with super continuum source on the left. This also was co-registered with an interferometer. This allowed us to do double pass interferometry and spectroscopy calibration, as well as phase retrieval, all in one very simple test bed. And we were able to simulate either an open aperture, a shaped pupil chronograph, or the unobstructed Raman telescope, any of those using what we call our emoji mask for obvious reasons. Oh, and I forgot to mention, that's an example of the shaped pupil PSF on the bottom left, showing that the PSF cross sections and how they change in the X and Y axes. That actually has an effect on the 45-degree dispersion mode as compared to the linear ones. So just a note there. So in that test bed, we one of our first, of course, important calibrations is verifying the wavefront for pre and post environments. This is just showing that we actually got the same wavefront that we aligned it to in the double pass interferometry, and that pre and post environments, we got the exact same result as judged by phase retrieval. And this is just a model fit that Hart put together for us to show a very good comparison between the two. All right, these are some of the key calibrations that we did at Goddard. On the top, you can see a walkthrough of the dispersion calibration. We need to actually calibrate that linear dispersion curve. We're careful not to call it resolution at this point because we don't have the actual point spread function in its true final fit and form on the instrument, which I'll get into in a minute. But the way that we calibrate dispersion in these modes is we actually walk through wavelength, and then we fit that out in our models from there. On the bottom is actually the polarization mode, which of course by design has very little to no dispersion, but had very tight requirements on the degree of polarization suppression in orthogonal states. So you can see us blinking through and proving that we do split and then suppress orthogonal polarization conditions. That's all real lab data, by the way. You wouldn't believe it from how perfect the PSFs are. All right, now, so starting to move forward into the ground calibrations, we have to think carefully about what we actually needed to do on the ground. So the two key things that were instrument level requirements we need to be careful about was the tolerances on the final spectral resolution and the wavelength accuracy. This was particularly important, and that's actually one of the reasons why there are so many narrowband filters in addition to the wavefront sensing that we have to do. It's because we now have a deployable slit. So we actually drove some of the narrowband filters to get the wavelength accuracy that we needed. So those narrowband filters are used in spectroscopy on orbit to pin the 0 point of the spectrum that we get anywhere on the detector because it's a deployable slit spectrograph. So we have to do both these things. We have to calibrate them at the instrument level. And they're both dependent on some very key instrument parameters. You have to have the right actual instrument pupil. Sidebar on that is that an interesting systems engineering side effect is that at the instrument level, we're actually able to have greater confidence in our CVE of the as-built spectral resolution because the appetizer actually defines the pupil function that you're going to see on orbit. So assuming everything goes well, at the instrument level, you actually have great confidence at the observatory level spectral resolution that you're going to get. But in any event, the test that we had decided we really needed in TVAC2 was dispersion calibration with the final flight pupil, and also calibrate the narrowband filter transmission. This is really one of the key ones because it's an angle of incidence dependent term. So if we had any of those bias terms from the as-built angle of incidence or anything else about those filters come in, that could have given us some trouble. So first thing we had to do is prove that we could do that with the equipment that we had. And so this is an example of actually hitting that tolerance right here with a narrowband filter scan. So we had a 2 nanometer in roll up. Our entire wavelength accuracy requirement is 2 nanometers, which is actually not, you wouldn't think that's very aggressive, but when you decompose that into everything and every single error budget, including all of the astrometry tolerances that you have, because now with the deployable slit spectrograph, you're pointing on your slit couples into your wavelength accuracy. So we had to be very tight in our actual filter calibrations as a result. And here is showing an example of a Bruker scan at Goddard, and then an actual measurement of a spare filter on our test bed. And then when we forward model the actual dispersion profile of the test equipment we have, we can then take the red dash curve, map it to the black curve, and show that it matches the actual Bruker at that exact same angle of incidence to an extreme level of precision. So with that, we knew we could move forward and do that to as many of the filters we could get away with, at least in CGI during TVAC. So this is just an overlay of all of those measurements. The key filters are 2C and 3D, which have the blue plots as well. So those we actually did some very careful characterizations of those. We decided part of the reason why we did some of this work is we weren't super happy with all of the measurements that we got from the vendor. So we decided to be careful, remeasure them again. And what you can see is that we actually have very good agreement between what we scanned with the Bruker in a calibrated spectrometer, what we scanned in TVAC. And they agreed very well, which is as much a testament to how good of a job Brian and company did to aligning the filters to the nominal angle of incidence as anything else. So we have that now, and we know for sure that that'll be okay. So we actually did also try to do as many of the filters as we could. They weren't all critical. We didn't get to all of them, but it looks like we have all the data we need to give us the confidence we need in every narrowband filter we could use. The two key ones really are 2C and 3D for hitting the spectra on the detector on orbit. Getting to the dispersion, we had a level 7 requirement that we hit a particular spectral resolution. So this is actually we decompose that into 2 steps. One was the linear dispersion without the instrument pupil, and then the other one was the actual spectral resolution. So this is showing what our linear dispersion had to be, which is 204 nanometers per millimeter. And we decided to tolerance that against what wavelength that hit, just because we knew that it was a sliding curve where that parabolic shape of the spectral resolution was going to land. So we hit that very well, pretty much dead on. And then the spectral resolution that we estimate in the slitless condition during TVAC was very similar. We actually got 724.4 nanometer wavelength where we actually hit that R50 crossover point. So in that, we had to hit to a 10 nanometer tolerance, which we easily hit. So something important to note here is that this was actually a slitless point spread function, but the slits in CGI are really intended for speckle suppression around that PSF. They don't change the line spread function too much. So this is actually a relatively fair assessment of what we think we can do on orbit. Right. So since we're late, I'll say thank you. And that there's similar data for band 2.
I don't think people appreciate how small these things are.
That's an interesting. So
yeah, I'm sure you do. But the first time I saw it, I was like.
So that entire DPAM plate is like the OG iPhone basically in size, which is interesting because that means that about. The joke is that even though they all fit in the palm of my hand and we brought them in a suitcase, it's like 20 or 25% of all the optical elements in Roman. So there's really a lot crammed into here. And actually that, we didn't get into this at all. There's a huge amount of technical development that went into making that DPAM possible at all in just packaging and launch survival. So took years of work.
Just one second. It's very impressive that around this time when we had this GITL exercise that Eric mentioned, and we had trouble fitting around PDR, that was another, D-scope that was taken, and it was just really impressive that we were able, to recover the spectroscopy and a lot of credit belongs to you and Tyler and the team. It's just really great teamwork, and so it's impressive that not only we were able to fit the hardware in, but also to test it and characterize it a bit in the TVAC. It was not a requirement; it was a goal, but it was done by the team. So thanks everybody.
Yeah, everyone did a great job.
Thank you, and I want to add that because Roman CGI had this constraint, we're not able to fly the IFS. Or we put a slit prism in here and make a recommendation to have world to do this spectroscopy trade earlier, IFS or some other ways, different detectors, and it's going to drive instrument performance, mass, power, technology investment early on. So think about this trade early.